What's going on, everybody? We are now moving in to our portion of the notes over organic structures. This is where it's going to start getting a little bit weird. The first major rule, and the thing that you have to know, and if you go and take organic in college is going to be a thing you're going to learn really quick, is about skeletal organic structures. And because some of the structures that we deal with in this class are absolutely massive, we just need another way of writing them out. We can't just do a Lewis dot structure where we draw every single atom and draw a line connecting all of them and you draw the dots around. That just will not work for the structures that we're doing. So we have another method. This technique involves using straight lines to represent bonds between carbon molecules. And then you just add in the pieces that are not carbon. Kinks or dots are added to the chain to represent additional carbons. So like instead of just having one straight line, if you want to have 3 carbons, you would go 1, 2, 3, or if I get a piece of paper here. Again, I hope I'm in frame. So a straight line without that little curve at the end would just represent 2 carbons connected to each other. This would be 3. If you do zigzags, as your pen dies, you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. So you add in kinks, or if you for some reason can't fit them in there, you can do things like this, and that would represent, again, I hope I'm in frame, 1, 2, 3 carbons. I'm working on getting something where I can actually write on the page, so hopefully that comes up soonish at least. And then you just go back and assume that every single carbon had to be bonded to 4 things, so hydrogens were just filling in the blanks. Basically, the way to think about it as the meme shows, even though hydrogen exists, when you're drawing a carbon framework, you have no place in the story. You come from nothing. You are nothing. There is no reason to be drawing hydrogen when it's attached to a carbon. If it's attached to something else, you do still want to draw the hydrogens. You'll see what we mean by that in a little bit, though. So, for example, this is a hexane molecule. So go ahead and in your notes or whatever piece of paper you have lying around, try to sketch it. I would actually even recommend write out this full thing, write out the full C6 with all the H's attached to it, see how long that takes you, and see how long it takes you to actually write the full structure. If you want to go ahead and pause just to make sure you're doing it correctly, you can. So I'll give you a moment. I assume you would have paused by now if you wanted to. So for hexane, all you have to do is what I usually do when I'm drawing these is I go start with a dot wherever I'm positioned. So that's 1, 2, 3, 4, 5, 6. There are 6 carbons in that chain. This one right here. So that is hexane. And I assume that took you significantly less time. Again, each of the points of the kinks in the chain represent a carbon. All of the points where it's bent will represent there's a carbon there. And then we just assume that there has to be hydrogens filling in all the gaps. Using this technique, hexane goes from that to this, or occasionally the in-groups will be labeled. This just depends on where you're drawing it from or what specific type of chemistry you're doing. In this case, see we've got our 1, 2, 3, 4, 5, 6. Again, the lines don't represent carbon. The lines represent the bonds between the carbons. So here is one. This straight line would be connecting 2 carbons, so there has to be 1 here and 1 here. This line represents connecting them, so there has to also be 1 here. This represents connection, has to be 1 here, has to be 1 here, has to be 1 at the end. 1, 2, 3, 4, 5, 6 carbons. So structures like this is why we need to have skeletal structures. They can be a bit tricky at first, but it takes something that would have taken you 20 plus minutes to do a Lewis structure of something like this absurd monstrosity that's up here right now. But it would only take you a couple of minutes to get it done if you're doing the skeletal structure. It still takes a little bit of time, and usually we're not going to work with structures this big because it's just not reasonable. It's not really useful. But skeletal structures are going to be most of the time what we're going to be doing in this class. Now, even with that out of the way, even with covalent bondings, there are actually different versions of covalent bonds. Specifically, these are referred to as sigma bonds and pi bonds. And you will notice up the top here, because I want to make sure that my incredible humor is noted, this is not normal bonding. This is advanced bonding. We're going pretty well beyond what you talked about in general chemistry. So when you picture a double bond, what do you see? And what about when you do a triple bond? I'm going to make sure I know what's on the other slide. So I assume you pictured stuff like this. Single bonds, like a line connecting them. Double bond is like 2 lines, and a triple bond is like 3 lines. And if you do picture that, great job. You paid attention to my earlier versions of the class. I also lied to you, though, because that's not actually really going to be what's happening. So while single bonds function in a similar way, single bonds are for the most part going to do that. Double and triple bonds are different. We know that covalent bonds are formed from sharing electrons, but in reality they also involve orbitals overlapping. So you might have been wondering why we talked about orbitals. Well, if you have, for example, 2 hydrogens that are bonding together, they are each in s orbitals. Their electrons are each in their s orbitals. And so when they smush together, you will get a hybrid s orbital. Both of their s orbitals will smush together, and their electrons will be going around both of the hydrogens, and that is what's connecting them together. You could have the same thing happen with an s and a p orbital, so this would be hydrofluoric acid. The hydrogen and one of the lobes of this f orbital will bond together, and you will get, it's still got this lobe, but now we've got this weird sp combo orbital thing going on here. Or you can have 2 p orbitals, and the 2 p orbitals will have their kind of lobes of their orbital will touch each other, and they will cause their electrons to freely flow between the 2 of them. So you can see that single bonds are still linear. They're still going in a straight line. These bonds are called sigma bonds, and they are represented by this little circle with a hat on it. Is usually how I remember it. And they are a straight line. They are exactly what you expected. If we flip back here, that's a pretty good representation of here. We just don't draw the bubble kind of going around it where all the electrons would actually be found at. And here's a kind of another one. Notice that it's not only the carbon-to-carbon bond that's a sigma bond, but also the carbons and the hydrogens. This kind of bubble between them where they're blending their space together. And this one, it's the nodes overlapping, and this one, it's just kind of comes in and bubbles. It's red, so it's kind of hard to see, but it comes in and it bubbles out here because they are hybridizing the bonds. They are kind of combining them together. So that's sigma bonds all around. A single one of these covalent bonds in this case is a sigma bond. But what about double or triple bonds? Why do they not work like this? Why are they not just going to fall in line and just also connect side by side with the single bond? Well, we know that carbon can undergo double and triple bonds, but there isn't really space there. If you remember the rules of our electron orbitals, if you go back to like the Pauli exclusion principle, Hund's rule, all that stuff, the Pauli exclusion principle says that every specific location can only be held by 1 electron. Even if it's in the same orbital, it can only have 2. They'll just differ by spin. So in this carbon-carbon double bond, there is the 2 electrons from each of these orbitals. They've combined together, so they each kind of have their own half. So there will be the electrons are in there being shared between them. 2 electrons. So the 2 electrons are moving back and forth in this one orbital. There is no longer space in that orbital for more electrons. Every orbital can only hold 2. And this is a combined orbital. It's weird. It's not a normal shape of it, but it is one orbital that's connecting those 2 together. So we cannot put another one in there. They cannot occupy the same space. So if they can't go in that middle, in that gap, we need to figure out where they're going to go. So we also need to consider the orientations of the orbitals when we're making our bond. Which of the electrons will be doing the bonding, and what shape do those electrons have? Well, the valence electrons, the outermost electrons, are always either s electrons or p electrons. We know this because if you look at the periodic table, which I haven't gotten things more prepared since the last video, I apologize. But if we go and look at our periodic table again, I really hope I'm in frame. These are going to be really awful if I look back and find out I'm not in frame, but whatever. S orbitals are starting on energy level 1. P orbitals are starting on 2. D orbitals start on 3 and F orbitals start on 4. So in the first row, these are all energy level 1, that's S. The second row, there's S's and then P's. Third rows, there's S, P's, and then the d orbitals will get added later, but they won't be outside. They'll be back in the third energy level, but by that time, we will have gone and put electrons in the fourth energy level. So only the S and P electrons will ever be involved in bonding because they will only ever be the ones on the outside part of the atom. So the orientation of an S shell doesn't help us because we just talked about you just rotate a sphere. It doesn't do anything. But the P shell actually may give us some insights. So if you remember, I'm going to get a couple of pencils and markers and stuff here so I can kind of represent this. So our P orbitals can go, and I throw things all over the place. Whatever, I've got 3. So our P orbital can go in 3 possible orientations. We've got in and out, side to side, and up and down. But if they connect, if, for example, 2 adjacent atoms connect with their p orbitals and they overlap here and they get kind of stuck together, there are still, on each of them, orbitals going up and orbitals going in and out. The orbitals are oriented on perpendicular axes. So the p orbital lobes will actually align with one another. While the bond is going flat right here, and this would be much easier if I had like my writing thing. I may have to do a little bit of stuff, and we'll talk about this in class, so those of you in class will be able to see it more. If you have questions and you are one of my AMI kids, let me know, and I will try to find some other stuff to help make this make a little more sense. But basically, the p orbital lobes will align to one another, and that will make a rigid structure to form a double bond. Or if it's 2 sets of p orbitals, it'll be a triple bond. We call these aligned p orbitals pi bonds. Way easier to remember because it's a p orbital. You could also think of sigma bonds as s orbitals, and that's why it's the first one, and then the p orbitals, there's more of them, so and that's why you can have 2 extra ones. But here's kind of what's going to happen here. So your first carbon-carbon bond, this one right here, is a sigma bond. They have just interacted and they're sharing their electrons. There are 2 electrons bouncing back and forth here. But these pi bonds will form between these 2 p orbitals. They're going to be positioned vertically, and if they line up together, if they are in the same position, they will kind of bend towards each other slightly, and you will end up sharing the electrons in those p orbitals. And the 2 electrons will be bouncing and going back and forth around in that circle. Now, the important part about this is that this is going to make them locked. Triple bonds follow the same process. We've got the sigma bond connecting them here. In this case, these red ones right here are going to orient themselves or lock themselves in, and then the blue ones will lock themselves in. Once you've made it a double bond or a triple bond, you have basically created a cage around it. When it was just the 2 that were here together, you could kind of move them around and they could kind of bend and flex a little bit more. But now that you've gotten these things oriented around it, they are locked in place, which means 2 things. Number 1, that bond is no longer going to be flexible. That bond is no longer going to be mobile around a surface of something. And number 2, that means you now have these areas that are just poking out of the sides of the bond loaded with electrons. And like we've talked about, electrons are the things that cause reactions to happen. So because these electrons are all floating around here on the outside, they're kind of stuck out. It's almost like a flag waving around saying, you should react here. I have lots of electrons. And it's a great place for electrons to be taken away or for electrons to move when you're looking at a bond. So determining number of sigma and pi bonds in a structure is now super easy because you know how the bonds are made. So every single bond that there is there, every single bond, like not every single, but every single bond, every bond between only with one connection, one overlapping. I guess it's a little confusing. Every single bond is a pi bond. The first is a sigma bond. Man, trying to talk too fast. The first bond made in every kind of bond that is formed covalently is a sigma bond. And every additional bond is a pi bond. So let's look at this really scary structure from before. Let's count how many sigma bonds there are and how many pi bonds there are. Now, the only important thing to note is remember skeletal structures are hiding the hydrogens from you. So what we're going to do first is we're going to go through and we're going to count all the ones we can see. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. Plus these 3 would be 38. Plus these 3 would be 41. Plus this hydrogen here would be 42. Plus these 3 would be 45, 46, 47, 48, 49, 50, 51, 52. And then we have to check if any of these need hydrogens. So for example, let me write down 52. If it wasn't actually 52 and I've already lost count, at least you get the idea of this. Most of the ones you do won't be this difficult. So this intersection here is connected to 1, 2, 3, and then there's a double bond, so 4 bonds, so there's no hydrogens there. But this one is 1, 2, 3. There needs to be another invisible bond here because hydrogen or carbon needs to be bonded to 4 things. That means that there must have been a hydrogen there. So that is an extra 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I believe, and again, I may have miscounted because I was just doing this on the fly and I didn't actually do this ahead of time, but I believe there are 65 sigma bonds in this structure. And then for pi bonds, we just go and count all of the additional bonds beyond the first ones. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 pi bonds. Done. Now, I'm going to be pretty lenient on the counting because it can be kind of hard to actually count them. Getting off by 1 or 2 is not that big of a deal. As long as you get the broad concept that all of the double bonds count as 1 sigma and 1 pi, and all the triple bonds count as 1 sigma and 2 pi, you should be good. So this is the last thing that I want you to do in your notes, I believe. Make sure I've got this. So this is a structure. This is a Lewis dot structure for a formula. It's for 2' deoxycytidine. And go ahead and I want you to try to turn this into a skeletal structure and then identify the total sigma and pi bonds present in this structure. So this is kind of your assignment for this, just as a double check. I will show you at least what the thing looks like in a moment. I do want you to do this beforehand as practice before I click over to the other slide and show you what the correct answer is. Pause the video now if you need to. I think I've blathered enough since I said you should pause the video if you need to. So we're going to go ahead and we're going to move on to the last slide. So this is what your thing should look like, I believe. I think the angle is a little off. Oh, wait, no, sorry. I don't think this is the right one, actually. Well, I'm already on the slide. I'm not re-recording this lecture. So this is another example of one. I will just post it. I will make sure that it's posted somewhere online, or if you want to check it in class or send me a picture of it, I will do that. Let's do that, actually. I'm probably going over this in class anyway, so you'll get to see what it looks like. But for you who are on AMI, go ahead and just send me this picture if you want me to check it, if you're not confident. This is a second one you can try if you would like to try it. I don't know why that was on there. Oh, well, you'll live and you'll learn. Anyway, that brings us to the end of our advanced structures for now anyway. We're going to talk about advanced geometries in our next section, but that will probably not be until next week. If you have any questions, especially at the end here, because I got really confusing because, you know, I try to do all these in one take and I don't know anything about video editing, leave them in the comments on this, or you can send me a video or send me an email, or you can send me a video. But you can send me an email. You can hop into Zoom during school if we have free time, or after school, or you can come in on the Friday Zoom and you can ask questions then. Anyway, I hope that makes sense. Hope you have a great day, and I hope to see you here from me soon.